This is all the information. It will be in the IMPA webpage, www.impa.br, in the part events. Okay, so now that I made the advertisement, let's see, I should be able to come back here. The Control L. Wow, I managed. Okay. 26 and a half. Okay. So good morning again, and thank you for staying here for the fourth talk in the morning. I will tell you today about a project that started 11 years ago in Stony Brook, and it goes about the Mandelbrot set and its satellite copies. So, as everybody here knows, probably, for any quadratic polynomial, p c zeta is zeta squared plus c on the Riemann sphere, infinity is fixed and super attracting, so it has a basing of attraction. And we can define the field Julia set to be the complement of the basing of attraction of infinity, so the set of points with bounded orbit. And the Julia set, which is the set of points with chaotic dynamics, is the common boundary of the field Julia set and the basing of attraction of infinity. Here, I drew some example of field Julia sets, and you can see that some are connected and some are not connected. And then you can define the set of parameters such that the field Julia set is connected. This is called the connectedness locus, which in this case is the Mandelbrot set, is this guy. And a very fascinating fact about the Mandelbrot set is the fact that there are little copies of himself inside himself. For example, if this is a zoom here, and you can see that this looks like the whole Mandelbrot set, just here is smooth, the Mandelbrot set here has a cusp, and here it's a zoom here. And you can see that this guy looks exactly like the Mandelbrot set. This lives here up, and this lives here. And just looking, we can see that these copies of the Mandelbrot set come in two different flavors. Some have a cusp, and some don't. And we call the copies with cusps primitive, and the others satellites. Satellites, I guess, because they are attached like satellite around the main, around the Mandelbrot set. And the presence of these copies is explained by the theory of polynomial-like mappings, which was developed by Dewey and Hubbard in the early 80s. So, what is a polynomial-like mapping? A polynomial-like map, as the name suggests, is an object that behaves as a polynomial in a neighborhood of its field Julia set. So we defined the field Julia set for a polynomial as the complement of the basing of attraction of infinity. So on a neighborhood of its field Julia set, the polynomial expands because all the points outside goes to infinity. So a polynomial-like map is an object that expands. More precisely, it's a triple. A degree D polynomial-like map is a triple F U prime U, where U prime and U are topological disks. U prime compactly contained into U, and F maps U prime to U properly, holomorphically, with some degree D. So here you have a picture. You have your disk U prime that is mapped properly holomorphically to U that contains him compactly. Every degree D polynomial restricts in a neighborhood of its field Julia set to a polynomial-like map of the same degree. But this is not a exciting example. To find a not a trivial one, let's look, for example, to the parameter of the Mandelbrot set here. Just, we are here. This point, it's here up in the Mandelbrot set. That point. The Field-Julia set looks like this. The critical point is more or less this point in red. And its dynamics is this one. It does go up, pa, 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 and comes back. So the whole component, this little disk, goes here up, 2 to 1, because there is the critical point. Then it goes here, 1 to 1, because we don't have any other critical point, so we are conformal. Then it comes back down, 1 to 1, and comes back here, 1 to 1. So this component is mapped to itself 2 to 1. And if we take a neighborhood of this component here, remember outside we have the basing of attraction of infinity. So after the fourth iterate, comes back, it does pa, 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 but a little bit bigger. And this degree 4 polynomial, because I mean the fourth iterate, 2 to the 4 polynomial, because it's the fourth iterate of degree 2 polynomial, has a degree 2 polynomial-like restriction here. This is an example. And why am I telling you about this? Because Duadi and Hubbard in 1985 proved a very important theorem, the straightening theorem, that says that every degree D polynomial-like map is hybrid equivalent to a polynomial of the same degree. Hybrid equivalence is a quasi-conformal conjugacy which has D bar equals 0 on the Field-Julia set. And by the way, how is defined the Field-Julia set of a polynomial-like map? For a polynomial, the Field-Julia set is the set of points that doesn't go to infinity. Here we define it in the same way, just we don't have an infinity. So the Field-Julia set is the set of points that do not go away, stays there, that you can iterate forever and ever. In this example, the Field-Julia set is this black component, this little disk. And the straightening theorem tells you not just that every degree D polynomial-like map is hybrid equivalent to a polynomial of the same degree, but this member is unique if the Field-Julia set is connected. And this uniqueness allows us to speak about parameter planes. What do I mean? Let's now consider a family of quadratic-like maps. This is polynomial-like maps of degree 2. Parametrized by some lambda in a big lambda, which is a disk, a topological disk. And let's say that this family depends holomorphically on lambda. So for every polynomial-like map F lambda, everybody has a Field-Julia set K lambda. And then this Field-Julia set K lambda is either connected or not. And then we can define the connectedness locus for this family as the set of parameters, the set of parameters lambda such that the Field-Julia set K lambda is connected. And then the uniqueness of the straightening theorem of the previous slides allows us to induce some map between parameter plane that goes between M lambda, the connectedness locus of the family of polynomial-like maps, to the Mandelbrot set. Why? Because to each parameter lambda here, we have a unique polynomial associated to it. So the parameter plane straightening map, chi, goes between the connectedness locus of the family of quadratic-like maps to the Mandelbrot set and associate to each lambda the C such that F lambda is hybrid equivalent to PC. Yes?
An index, but then lambda is also a variable. So do you mean to say m sub capital lambda? Like,
No, I mean, the parameter lambda goes to the parameter C. This map goes between parameter planes.
but the definition of m sub lambda.
Ah, sorry. Okay. So call it m twiddle. It's m lambda because it should have been m little f. Sorry. It was for saying that is the connectedness locus of the family of the quadratic like f lambda. Sorry. Okay. And Duody and Hubbard in that paper on polynomial-like maps also proved that under very reasonable conditions, among which the connectedness locus of the family being compactly contained in my parameter set, then this map chi is a dynamical homeomorphism. Dynamical because each parameter goes to the parameter such that in the dynamical plane we're conjugate. Okay? And a remark that will be very, very, very important later is that this map is actually holomorphic on hyperbolic components. This is components where we have an attracting side. Okay. So why do we see copies of the Mandelbrot set inside the Mandelbrot set? Well, if you remember, this guy, this parameter gave us this field Julia set, which had a degree 2 polynomial-like restriction here. And this guy is a hybrid equivalent to this guy. So this parameter goes here to the center of the Mandelbrot set. But if I move a little bit here, for example, I take this parameter, I say this guy. And here I have a quadratic-like restriction here around, where we are hybrid equivalent to this guy here that lives here. And we keep going. I mean, there are infinite of them, so I mean, I will stop here. But we can take a quadratic-like restriction for everybody in a neighborhood of the connectedness locus of this family of quadratic polynomials, quadratic polynomial-like maps, where the connectedness locus is the little copy of the Mandelbrot set. And since this little copy is compactly contained in the set of parameters that will be a disk here around, we have that the parameter plane straightening between this guy, the copy, and the Mandelbrot set is an homeomorphism. And this is why we see a copy. It's actually a homeomorphic copy. So every polynomial, quadratic polynomial in a neighborhood of a primitive copy has a polynomial-like map restriction of degree 2. And so primitive copies are homeomorphic to the whole of Mandelbrot because of Duody and Hubbard. Lubitsch in 1999 proved in another amazing paper, proved that this homeomorphism is actually quasi-conformal. Which is, I mean, these shapes really looks like these shapes, so it really makes sense. Okay, so this is the story for primitive copies of the Mandelbrot set, the ones that have a cusp. What happens with the satellite ones, the ones that do not have a cusp? These guys, let's remember that we have this kind of copies, the primitive ones, and the satellite, they're these ones. To understand what's going on with satellite copies, let's first say briefly how the satellite copies arise. This guy, the main cardio, or the main hyperbolic component, is the set of parameters C such that my polynomial, my quadratic polynomial, has an attracting fixed point, the alpha fixed point. And here you see drawn, attached, other hyperbolic components where I have a attracting cycle of period, the denominator, for example, here 2, and the rotation number, this index. For example, here 1/3 and here 2/3. What does it mean? Here, everybody has an attracting cycle of period 3, and the cycle moves one to the other, to the next one. Here, everybody has an attracting cycle of rotation number 2/3. So we have an attracting cycle of period 3, but everybody doesn't move to the next one, but moves to the one after. Well, let's make a draw because in other cases it's incomprehensible. Good morning. Here we have our hyperbolic component of rotation number 1, 3. Everybody here, every parameter here has an attracting cycle of period 3 and rotation number 1/3. So I move here and then here and then here. Well, if I'm going here downstairs, everybody has a periodic cycle of period 3. It's actually here down, but it moves it skips the next one and goes the one after. Okay. And then was like that also before? Well, whatever. Do you see fine? Okay. Okay. So what happens? It happens then when my attracting fixed point goes in the direction of one of these hyperbolic components, let's say here, it gets closer and closer and closer to a repelling cycle of period 3 in this case, and rotation number 1/3. At the point where these two components touch, the alpha fixed point and the cycle merge together. They become one thing, a parabolic fixed point. And when we go in the hyperbolic component of rotation number 1/3, the alpha fixed point becomes repelling and the periodic cycle becomes attracting. And here in all the parts. The parabolic parameter at which the satellite, this hyperbolic component is attached to the main cardio, it's called the root of the satellite copy. And the index is the rotation number of the copy. Okay? So what happens in my satellite copy? If I take a parameter here, I have my period 3 cycle, and I can take a polynomial, degree 2 polynomial-like restriction in a neighborhood of this year. And the same I can do here more down. But when I get to the root, I cannot do this anymore because the root is parabolic. So if I take any neighborhood of the year and I take the third iterate, here everything is fine, I'm compactly contained, but here I have the parabolic direction. So I do something like blah, I go out, and blah, I go out. So we are not a polynomial map anymore. And here the theory breaks. It doesn't work. So what do? Well, we like compactness, so we take away a neighborhood of the root, and we apply the previous algorithm. So by Duady and Hubbard, the satellite copies of the Mandelbrot set are homeomorphic to the Mandelbrot set outside any neighborhood of the root. And by Lubitsch, this homeomorphism is quasi-conformal. Then in 2000, Peter and Siski extended this homeomorphism also to the root, but without dynamical meaning. I mean, it's not a polynomial-like map. And just a remark about the parabolic roots, they all have the same dynamics. You can construct another kind of restriction that is not polynomial-like. You can call it parabolic-like because you don't have fantasy. And you can prove that there is restriction of the Q theta rate here around, such that on the ear, they are all hybrid equivalent. They all have a common model, which in this case, it's the root of the parabolic Mandelbrot set. But this one will be another talk. This one is just to say that all the root of satellite copies dynamically have restriction which are hybrid equivalent. Okay? So, what did we say so far about satellite copies? That if I have a satellite copy, I know that it's homeomorphic to the Mandelbrot set outside any neighborhood of the root. And this homeomorphism is quasi-conformal. So if I have two satellite copies, let's say this guy and this guy, I can compose the 2D Hubbard parameter plane homeomorphisms going from the satellite copy to the Mandelbrot set and come back. So I get a homeomorphism that goes between one copy and the other one. This homeomorphism is quasi-conformal outside any neighborhood of the root because of Lubitsch. And at the roots, dynamically speaking, the dynamics are conjugate, have restriction conjugate, quasi-conformally, hybridly actually. So the natural question is, this homeomorphism between satellite copy and satellite copy that is quasi-conformal outside the root, does extend quasi-conformally at the root? Each of these guys are differentiable here because of the, in the main hyperbolic component here, I mean, they are all little circles, the main hyperbolic component. So does this homeomorphism extend quasi-conformally at the root? Yes.
Satellites, in one case, it's a periodic point of period 2, no, joining, and so if you go through the left, it is a periodic point of period 2 that it was repelling and now it's attracting, and if you go up, it is a periodic point of period 3. How this?
But the parameter, okay, I guess I understand what you mean. Let's see. Here, dynamically, you have a periodic point of period 3. Here, dynamically, yellow, did I use it? No. You have a periodic point of period 2. But still, there is a homeomorphism between the whole guy and the whole guy. No, don't worry, because actually you gave the answer. And the whole guy and the whole guy. And you actually are composing these homeomorphisms. We know that there is no hope that the homeomorphism that goes between the satellite copy and the whole Mandelbrot set extends quasi-conformally to the root, because you cannot straighten a root, a cusp quasi-conformally. No way, you can't do it. But here you don't have a cusp. And here you don't have a cusp. So the idea is, here is not QC, and here is not QC. But if I look this directly, can I extend it QC? This is the question. And it's a reasonable question because they do look alike, right? I mean, geometrically speaking, they're kind of no cusp, no angle. So, more questions, by the way? No, I mean, I can explain. Okay. And this is just to say that, I mean, this remark is for saying that this was kind of expecting then this homeomorphism between satellite copies will be quasi-conformal at the root. In the wonderful paper of Lubitsch, where he proved quasi-conformality of satellite copies and of primitive copy and the Mandelbrot set and satellite outside the neighborhood of the root, he actually says that presumably the satellite copies all have a quasi-conformal model. So, does this homeomorphism extend quasi-conformally at the root? And the answer is yes and no. Actually, and the discriminant is actually what you were saying, Chabi. Depends on the period of the cycle. We proved with Carsten. By the way, everything I'm saying so far is joint work with Carsten Petersen. I forgot to say it at the beginning. If the satellite copies, if the homeomorphism between the satellite copy P over Q and big P over big Q have a denominator of the rotation number different, which means the cycle has a different period, then no way. You cannot extend quasi-conformally your homeomorphism. Actually, the K, the dilatation of the quasi-conformal dilatation of this map goes to infinity, tending to the root on the center of Mizurevich spirals. So no way. On the other hand, if the rotation numbers have same denominators, meaning if the period is the same, like the rabbits all have the same number of years, then yes, your homeomorphism, your quasi-conformal homeomorphisms extends quasi-conformally to the root. Okay. Are there questions so far? Yes.
One is there some way, like some qualitative picture that you can draw to explain the first theorem? So like how do they look different? So for example, a cusp certainly is not quasi symmetric to around the edge, right? So that's why you can sort of tell that the satellite copy won't be quasi-conformally equivalent to the full copy of the Mandelbrot set. Is there some way we can sort of convince ourselves visually that if the periods are different, that they will not be?
Yeah. I had the pictures, but in a different talk because I was going to speak about the positive result, not the negative one. But what happens? It happens that when you go to the root, I mean, let's remember that on my hyperbolic component, on every hyperbolic component, so in particular in the main hyperbolic component, my map is holomorphic. So no problem there. The problem is outside. And we know that we have Mizurevich points that here up are nice and straight, but the more you go here, the more they get spiraling, and then here they spiral a lot. And Tanley proved that at Misurevich's parameter, the Mandelbrot set is asymptotic to the Julia set. And these spirals spiral, go around with a rate that depends on the multiplier. And the multiplier of the alpha fixed point, which is lambda to the q. No. In the boundary of the main component, you're happy. The problem is what there is attached. The decoration, the Misurevich, well, I mean, maybe other points, but I mean, on the Misurevich point, we could make computations. And the point is that these spiral are self-similar, again for Tanley, and the ratio of self-similarity is this Q. So if the Qs are different, no way.
The context, your second theorem, and maybe the first theorem.
Like the logistical Mandelbrot? No, I mean, no, it's just quadratic so far.
So like if you have one parameter family, Mandelbrot like copy. Oh, I guess it's.
Yeah, but then it's a Mandelbrot. I mean, it's quite it's a Mandelbrot. Somebody else had a yes.
Yes, I have a question. So just seems that this particular map is not quasi-conformal, but is there another hope that there is some other map?
There is no other map that makes sense in the sense dynamically speaking. This is the natural one.
Okay.
This is a sensible one. But I mean, I don't know. They could be, but it wouldn't be dynamical.
And the second question, say you have capital Q divisible by Q. Is there a hope that the map you have will be quasi-regular? So is it true that the quasi-conformal constant will blow up in both directions?
I take these questions later. I mean, I ask if there was something to understand until so far because I didn't finish yet. I wanted to give an idea of the proof. Sorry. I wanted the picture to be clear. So now, how we prove these kind of things? Well, we want this map Xi. I'm always going to denote it Xi, the map between satellite copies. We want it to extend it quasi-conformally to the root. So we want that KXi, the dilatation, stays uniformly bounded. This is what we want. So what's the idea? The idea is, as Duadi-Dixit, do things in dynamical plane and plow. I have to learn this, how to pronounce it, harvest in and harvest in parameter plane. So what's the idea? Construct a family of uniformly hybrid conjugacy between correspondent quadratic-like maps. What does it mean? If I'm going between quadratic-like restrictions, I know that the restrictions are hybrid equivalent because they are both hybrid equivalent to the same quadratic polynomials. So I just compose and they are hybrid equivalent between them. And what I want is a bound on the dilatation of this quasi-conformal conjugacy, a uniform bound. And then I want to pass this bound, translate it to parameter plane. And just a fast remark about the negative result, looking for upper bounds, here we discovered lower bounds. Sometimes it happens. And in the case, the periods are different. These lower bounds go to infinity, go into the root? Well, I mean, you can find a sequence such that they explode, and then you need to write a paper and the epsilon and the delta, because I mean, the Stanley, it's the moral picture, but actually you need to make the computations. And then you can prove that if the periods are different, the map is not quasi-conformal. But to prove that the denominator are the same, the map between the satellite copies is quasi-conformal, what do we do? Again, we start taking a family of quadratic-like map indexed by my copy minus the root. Of course, the root is not a polynomial-like map. So let's say that these guys have lambda all living here in the 1/3 copy. And these guys have parameter nu all living here in the 2/3 copy. And we construct a family of uniformly hybrid conjugacy between correspondent polynomial-like maps. So we construct a family of hybrid conjugacy with a dilatation uniformly bounded. And I repeat again, we need to do this outside the main hyperbolic component. Because on the main hyperbolic component, everything is holomorphic and we're happy. And once we have this, we translate it to parameter plane by straightening a Lubitsch space of polynomial-like germs. A Lubitsch space of polynomial-like germs, it's, well, an infinite dimensional space that he proved having a product structure, internal classes that are codimension 1 manifolds and external classes, which are actually manifolds. And the problem is that on manifolds, making computations when the structure is given by Banach, Boles, blah, 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 is not exactly trivial. So what we do is that we straighten the external class to copies of C. Why? Because on C we can make computations. So we can pass the bound from here to there directly. Well, directly, modulo straightening these spaces. That is highly not trivial, and I won't speak about that because it will take 3 hours. Okay. So remark again, on a hyperbolic component, my parameter plane map is holomorphic. So the construction we need to make is out the main hyperbolic component. In the last 13 minutes, 12, wow, 15 minutes, I will give you an idea of how to construct this family of uniformly hybrid conjugacy between correspondent polynomial-like maps. So just to fix the ideas, because I don't want to lose you, if I'm in the center of my, let's say that this guy was the center of the main hyperbolic component. So here I have this cycle is super attracting. And the same was here. Where is the color I used is there. So the center, we put it here, more or less. So this cycle was super attracting. We know that we have our polynomial-like restriction, quadratic-like restriction. And my F lambda is hybrid equivalent to, well, if I'm in the center, I'm hybrid equivalent to the center, which is zeta goes to zeta square. And here I have the same, which is this. So I just pass from one to the other, I compose, and this is the map I called var-phi. Okay? Just to fix the idea. So I want this family of hybrid equivalences to be uniformly quasi-conformal. And the first thing that we notice is that my hybrid equivalence is not just quasi-conformal, it's hybrid. So the d bar is 0 on the field Julia set. So actually, I do not need the whole hybrid equivalence. It's enough to construct a uniformly quasi-conformal external equivalence. What does it mean? A family of quasi-conformal maps, uniformly quasi-conformal map between fundamental domains. So if this is my field Julia set, I can get an annulus. This is my polynomial-like map. I can get an annulus, call it A lambda, about my field Julia set, a fundamental annulus. So F sends the inner boundary to the outside boundary. The same for G. And I want a family C lambda of uniformly quasi-conformal maps between fundamental annulus that surround my field Julia set. Because of Riemann lemma, basically. Riemann lemma. Because then how you construct your hybrid equivalence, you take the hybrid conjugacy given by Dua D Hubbard on the field Julia set, and you know that that one has d bar 0. Then you take the external equivalence between the annuli, you pull it back by the dynamics, and you glue them together by Riemann. I mean, this thing needs to be an equivalence, not any quasi-conformal map between fundamental annuli will work. But if it sends, I don't know, the beta fixed point to the beta fixed point, then you're fine. Okay? So by Riemann, miracle, it's enough to construct a family of suitable fundamental annuli, A lambda, with a uniform quasi-conformal map between them. So how do we do it? Okay, we start by taking the external rays R lambda and R prime lambda, then separate the little field Julia set of my quadratic polynomial-like map to the rest of the field Julia set. So if my polynomial-like map, it goes here, this is my field Julia set. Well, let's make the construction on the blackboard because I made this slide for Pisa because I couldn't use the blackboard, but now I can, so I'm very happy. So this is F lambda. And this is G nu. We take, this will be the field Julia set, my little field Julia set, K lambda, and this is my little field Julia set, K nu. We have external rays, which there are blue, that separate the field Julia, the little field Julia set from the rest of the field Julia set. So pa and pa. And these external rays are actually sent one to the other by the Butcher map, the composition of the Butcher map, up to rotation. So we have a conformal map between these guys and these guys that respect the dynamics. This one was R lambda, and this is R prime lambda. R nu, R prime nu. Then we take a domain of univalency for the alpha fixed point, which is here, for the linearizer of the alpha fixed point. Why? Because we need to make computation at a certain point in life, sadly. We call it a d lambda. D nu. And we take some points in x lambda inside this domain on R lambda, x nu inside the domain, and on the polynomial map, yes. On R nu on the same potential. This is important, these 2 points. So the Butcher map sends one to the other. And the same on the other ray, x lambda prime. These two do not need to be in the same potential, but this guy needs to be in the same potential of this guy. Because the Butcher map will send this guy to this guy. Then we take their preimage under the polynomial map. So of zeta lambda, zeta prime lambda, here and here. And then we make a uniform quasi-conformal interpolation between these external rays. And how we do it? Well, this is, I managed to tell you in 3 minutes the biggest idea. This is the super highly not trivial part. Well, this is where the work is. How do we get to an annulus? Well, get your favorite equipotential. Okay, maybe not this one. Same equipotential. So E and E. Take a corridor. Here we have the preimage, right, of all of these. We take a line, I'm finishing colors, which is not good. Found another one. From here to my equipotential, that is sent to the same one by Butcher. And the same here on the other side. And then you take preimages. When you take preimage, what happens? This part gets the preimage of the equipotential. It's then I will show you actually a real picture. This guy goes here. This is the other preimage of this. This guy has a preimage here and a preimage here. This has a preimage here and a preimage here. And this line has the other preimages. One is here. The other one is here. Here. And here. And this is your fundamental annulus, which I will make white. This part. Here you have Butcher in white. And here is a problematic part because this part is the preimage of this part. And in this picture is all straight, but I'm lying. It's because it's difficult enough, this picture. But the problem is that outside the main hyperbolic component, you have the Q cycle that tends in a spiraling way. So here is where work is also. Seeing all of this with pictures, this is the interpolation between arrays. You take the lines in Butcher, you take the pre-images, and here is all given by Butcher, the blue part. Well, but this, what is it? Pink, orange, well, whatever this color is, here it's complicated. Why? Because the real picture is this one. Here I have, this is the pre-image of all this part. And here the Q cycle enters to the alpha fixed point, and then it's a mess. And then you have to deal with parabolic implosion. And I will just tell you, trust me, you can do it. Okay. And this is the interpolation between arrays, which we actually do all the way till the end. Then we take the fundamental domain we need. But yeah. So in the 5 minutes, no, I'm over time. 3 more minutes, okay. What, in the last 3 minutes, I will give you the main idea of how make this interpolation, which is interpolation is easy between, well, it's more doable between straight lines. So the first things we do is turning external arrays to straight lines. And in order to do it, we do the festival of change of variables. Here we have our polynomial-like maps, here and here. We start taking the linearizer. This is why we are in the domain of univalency for my linearizer. So here the dynamics is zeta goes to lambda to the q zeta. Then we take the logarithm. Then we normalize. Here the dynamics is zeta goes to zeta plus 1. And my external arrays are almost straight, but they do kind of like that. And then we straight them. We uniformize it to straight lines. We do the same on the other side. And then we have a well-defined map between these strips, between the boundary of these infinite strips, given by basically the Butcher map. You do the festival of coordinates back, Butcher, and then the festival of coordinates on the upper side and on the lower side. And then who is your uniform interpolation, quasi-conformal map between arrays? Well, just the linear interpolation. And how you prove that this map is uniformly quasi-conformal? Well, I mean, you're interpolating by straight line. If this 0 and zeta, 0 goes here, and zeta goes here, this line goes to this line. What do we need? We need the width of these strips to be comparable. So they have to be bounded by below and by above. They cannot do, and they cannot do. And we need this, the angle of the lines that here are like that, and then here like that, but we don't want that they become like this. So the slope is the word I was looking for. We need to bound the slope. How we do it? For bounding the heights, on one side is Beer's inequality, and on the other side, it's a module inequality. We consider that this guy, if I take the domain of univalency of the linearizer of the alpha fixed point, the lambda, I take away the alpha fixed point and modulo action of polynomial-like map, I get a torus, a complex torus. And this complex torus is isomorphic to C over the log of the multiplier zeta plus 2 pi I zeta. the map, the uniformization sends this infinite strip between the two rays till a straight strip, and the dynamics goes between zeta plus 1 and zeta plus 1. So if I take this infinite strip modulus zeta plus 1, a quotient by zeta goes to zeta plus 1, I get a cylinder, S lambda. And the modulus of this cylinder is exactly the height of this strip. And my map is basically straightening the cylinders, nothing more, nothing else. And these cylinders embeds in this torus. And this is why you have one inequality, is Beer's inequality. And this is also why you have the other inequality, because here you have Q minus 1 connecting components of the basing of attraction of infinity. And each of one has modulus pi over Q squared over log 2. So you know that this high is bounded by below and by above. And what do you do about the slope? You realize that this map, you can extend it because of you have the basing of attraction of infinity, you can extend it. So by compactness, the uniformizing map is nice. And then what you need is know here that if this guy goes to this guy, the distance between these points is not too far away. The problem is that you have no idea where that guy is. Because you have normalization, you can know where one guy is, for example, this one. The guy's on one ray, but not the guy on the other ray. But then you can use dynamics, and if I can normalize this point, for example, to be 0, I know that there is an iterate of this point that goes on this ray, and the same here. If this point goes to 0, there is an iterate that goes on this ray. And this allows you to put coordinates. And even though this iterate doesn't go to this iterate, they go, they belong between 2 points that goes to each other. So this point, this green point that I know where it is, doesn't go to the green point that I know where it is, but it's between 2 points that go to each other. And this is enough to make computations. And the distance of this point is bounded because of a lot of computations that I won't tell you. But this is how you do it. And you believe that you can do the part of parabolic implosion. And let's go to lunch. Thank you very much for your attention.
So in your main theorem, the quasi-conformal distortion, does it depend on P and Q or not? Or is it universal?
If Q is the same, is quasi-conformal. If Q is different, is not quasi-conformal. So it really depends on
But the distortion, the quasi-conformal distortion, does it depend on P and P prime?
We don't really compute. We know that it's uniformly bounded. I mean, of course, it does depend on those, on P and P prime, but I cannot give you something like, okay, if this is the P, then this is the distortion. No, till there, we don't get.
I think the question was, if you say Q, if Q grows between the same maps with the same Q, will the distortion grow to infinity?
Yes, yes.
But that, I don't know. So you have this map between two analyte, which is the conjugacy, I guess, of dynamics. And so on the white parts, it's clear it's a pull through of two dot-head coordinates. Then you have this linear interpolation between in the blue part. But why is this linear interpolation a conjugacy? Why does it respect?
It's not continuous. No. I mean, you have a fundamental domain, right? So I mean, you just need it's an external equivalence in the sense, I mean, okay. Here inside, this is a fundamental domain. So you don't have dynamics here. And this is a fundamental, well, domain. You don't have dynamics here. You know that where you have dynamics, it's on the array. And the part of the array is conjugate to the part of the array. And the part of the array is conjugate to the part of the array. And this is what it will give you, the fact that everything will be a conjugacy. But there, inside, is just an interpolation. It's just a linear interpolation.
Then let's